Welcome to my YouTube video today. The topic at hand is current electricity and is a topic in physics. First, I will take you through the fundamental law I intend using in the two problems I'll be solving today, and the law is called the Ohm's law. The Ohm's law gave us the relationship between the potential difference, or the voltage if you like, to be directly proportional to the current, and the resistance of the resistor. Okay, so V equals IR, where V is voltage, I is the current, and R is the resistance of the resistor, or resistors, depending on the amount of resistors in the circuit. The unit of resistance is ohms, the unit of voltage is volts, and the unit of current is ampere. I'll take you through the question. The first one, in the circuit diagram, calculate the ammeter reading. The ammeter reading, as you can see, this is the circuit diagram, assuming that the 6-volt battery has negligible internal resistance. In the second question, in the figure below, what is the value of the current I shown, assuming the cell has negligible internal resistance? Now to the first question. Looking at this question, the circuit has 3 resistors arranged in series. They are said to be in series because there's no breakage in the line of communication between the 3 resistors, so they are in series. The 5 ohm resistor, 3 ohm resistor, and the 2 ohms resistors all are in series. Okay, so the resistance of this resistor is 5 ohms, the resistance of this resistor is 3 ohms, and the resistance of this resistor is 2 ohms. So let R1 be 5 ohms, that's this, and then R2 3 ohms, referring to this, and then R3 be 2 ohms, referring to the resistance of this resistor. Now the total resistance R will now be the summation of the summation of the resistance of each and every one of the 3 resistors. Okay, so R will be R1 is 5 ohms plus R2 is 3 ohms, and then R3 is 2 ohms. Take note, any of these values of the resistance of the resistors can be the first or the second or the third, because addition is commutative. So irrespective of their position, provided you are summing up, you arrive at the same answer. So the total resistance of the 3 resistors is 10 ohms. Then the total voltage will be the summation of these 2 plus 2 plus 2. Okay, so V will be equal to 2 volts plus 2 volts plus 2 volts, which is equal to 6 volts. That's the effective or the total voltage or the potential difference through this circuit. Now from Ohm's law states that the voltage is directly proportional to the current, and therefore V equals IR. So once you remove the proportionality sign, you introduce equality and the constant of proportionality, which is the resistance of the resistors in the circuit. Making the current subject of the formula, if I divide both sides by R, I will be left with current here at the right hand side, and at the left hand side I will be having V divided by R, which is this. Therefore, the current or the ammeter reading in the circuit shown in this question will now be equal to the ratio of the voltage, the total voltage, which is 6 volts, divided by the total resistance of the resistors, which is 10 ohms, and this boils down to 0.6 ampere. 0.6 ampere. So the ammeter reading is 0.6 ampere. Is that okay? 0.6 ampere. Now to the second question. In this figure, you can see 3 resistors. 2 of these resistors are connected in series. And I will apply the method I used in the first question. If I christen the total resistance of the resistors in series as RS Rs would now just be equal to R1, which is the summation of 1 ohm, that's the resistance of this resistor, plus the resistance of the second resistor, R2, equivalent to 3 ohms. So 1 plus 3 equals 4 ohms. So the total resistance in series is Rs, which is equivalent to 4 ohms. It's 4 ohms. Now this 4 ohms and this 6 ohms are in parallel because there's a breakage in the connection here. You can see there's a connection here represented by this gray dot. Because of this connection, the current will move through the circuit quite alright, but this connection shows that the effective or the total resistance is series and these 6 ohms are in parallel. Because they are in parallel, the mode of finding the effective resistance is quite different from the mode of finding the total resistance in series. So in finding the total resistance in parallel, it will be 1 over RT, where RT stands for the effective resistance of the resistor in the entire circuit, which is the same thing as 1 divided by RS. I presume you know RS is 4 ohms plus 1 divided by R, and R is standing for 6 ohms. So if I impute RS and R, I'll have 1 over 4 plus 1 over 6. The LCM of 4 and 6 is 12. 12 divided by 4 is 3. 3 times 1 is 3. Plus 12 divided by 6 is 2. 2 times 1 is 2. Now 1 over RT equals 3 plus 2 is 5. 5 divided by 12. To find the total or the effective resistance going through this circuit, it will be the reciprocal of 5 over 12, which is same thing as 12 divided by 5. And 12 divided by 5 is 2.4 ohms. But I know that my voltage V, or the potential difference, is proportional to I and R. So if I make current subject of the formula, it will be V divided by R. R in this context is RT, that is the effective resistance. Voltage 6 volts. Total or effective resistance 2.4 ohms. 6 divided by 2.4 is 2.5 ampere. Hence, or therefore, the current I, you can see I here, is 2.5 ampere. So the current passing through this circuit is 2.5 ampere. So in the first question, I've been able to show you how to find the total or the effective resistance of the resistors in a given circuit when the resistors are arranged in series. And in the second question, I've been able to show you how to find the effective resistance of the resistors when they are arranged in parallel. And in both cases, we're able to use our formula, the Ohm's law, to find the current rating or the ammeter reading through the circuits. Thank you for watching my YouTube video. If you have any question, feel free to ask. Just send it to me through the comment section. Remember, the name of the channel is Victorian STEM, and if you have not subscribed, kindly hit the subscribe button. See you the next time.